This is going to be the last pre-lecture for the class, and the topic is colligative properties. And you're going to be learning, for example, why you can put salt on icy roads and that can cause the ice to melt. So in general, colligative properties are properties of a liquid that change when you dissolve some solute in that liquid. So in other words, they are physical properties of a solution that are different from the pure solvent with nothing dissolved in it. There are four colligative properties we're going to discuss. There's the lowering of vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure. And what we're going to see is that for all of these colligative properties, the extent of the colligative property, so how much the vapor pressure is lowered, for example, is going to depend on how many particles of solute are dissolved, so the concentration of solute particles, and it does not depend, though, on what the solute is. So we're going to assume that all solutes cause the same amount of colligative properties at a given concentration. Okay, so first of all, vapor pressure lowering. So we have learned about the concept of vapor pressure. That is, when you have a liquid in a sealed container at a certain temperature, there's going to be a certain amount of vapor above the liquid. What you find is that when you dissolve something in that liquid, the vapor pressure is lowered. So at the same temperature, there is less vapor above the liquid. And we are assuming that the solute is non-volatile. In other words, that it does not have a vapor pressure itself, like something like salt. Now you can mix two volatile liquids, such as alcohol and water, and then each one is going to contribute to the vapor pressure. That's a little bit more complicated. We don't have time to discuss that, but you can read about it in the textbook if you like. Now, I'm not going to do any calculations involving vapor pressure lowering, but I will move on to the next colligative property. Now, so we've learned that the boiling point of a liquid is the temperature at which the vapor pressure equals atmospheric pressure. So if you lower the vapor pressure at a certain temperature, that means you would have to increase the temperature to make the liquid boil. So the liquid is going to boil at a higher temperature than if there was no solute present. And so this is referred to as boiling point elevation. And there is an equation for the amount that the solute causes the boiling point to increase by, which we can call delta TB. And it depends on the concentration in molality. Remember, we use molality because it is independent of temperature. And so delta TB, the boiling point elevation, is just the molality times a constant known as Kb. So Kb is known as the boiling point elevation constant. It's going to be different for different liquids. You can see an example for water. It's 0.512 in units of degrees C per molal. So that means a 1 molal solution would increase the boiling point of water by about half a degree C. Now, if you're doing a calculation for a different solvent, you would just have to look up the specific constant for that solvent. So delta TB is the amount that the boiling point is increased by. So that means to calculate the boiling point of a solution, you take the boiling point of a pure liquid and then you add the increase to it. So for example, at sea level, water boils at 100 degrees. So if you calculate a delta TB of 1 degree, that means that solution would boil at 101 degrees Celsius. Now, at the same time that a solute causes the boiling point to be raised, it causes the freezing point to be lowered. So we call this freezing point depression. We have a similar calculation for freezing point depression. Delta TF in this case is just Kf times the molality. And so Kf is a different constant. It's the freezing point depression constant, which for water is just under 2 degrees C. So you can see that the same amount of solute has a greater effect on the freezing point of a solution than it does on the boiling point. Now, the other thing to keep in mind is that the freezing point is always lowered. It's never increased. So a solute increases the boiling point, but it decreases the freezing point of a solution. So to calculate the freezing point of a solution, you have to take the freezing point of the pure liquid, but in this case, you're going to subtract the delta TF that you calculate, because again, delta TF is always a lowering. Now, for example, since water freezes at 0 Celsius, the freezing point of an aqueous solution is always going to be 0 minus the delta TF. In other words, the freezing point of an aqueous solution is just the negative of the delta TF. And this picture from the textbook tries to explain why the solute lowers the freezing point of a liquid, and that's because you can see that the solid down here in the bottom right is a little bit less stable when it has solute impurities in it. In other words, it cannot form its solid lattice as easily. So the solid is less stable. That means it's easier to melt the solid. So the solid melts, or in other words, the liquid freezes at a lower temperature than if you just had a pure liquid. Now we can summarize the effect on the boiling and freezing points of a liquid by looking at the phase diagram. And so we learned about phase diagrams before. And so the green shows the liquid area for the pure solvent. Now what we have seen is that the solute lowers the freezing point, so that means the liquid solid line shifts to the left. And so in the light blue, you can see what it looks like for the pure solution. Now in terms of the boundary between pressure and temperature, now we can say that that curve represents the boiling point of the liquid at any pressure, but also in fact it's equal to the plot, it's the same as the plot of vapor pressure versus temperature, because remember when a liquid is boiling it means that the vapor pressure equals the outside pressure. And so we saw that vapor pressure lowering means that this curve is shifting down, so the vapor pressure is lower at a given temperature. So you can see the net effect, the overall effect is that we're increasing the temperature range at a given pressure over which the substance is a liquid. So a solution freezes at a lower temperature and it boils at a higher temperature, so there's a greater range of temperatures over which the solvent is a liquid. The fourth colligative property is called osmotic pressure, and so this is the concept of osmosis. So if you have two solutions caused by what's referred to as a semi-permeable membrane, then osmosis causes water to go into the more concentrated solution. So a semi-permeable membrane, it's a special material. As you can see in the picture here, it has some small holes in it. And those holes are big enough to allow water molecules to go through, but solute cannot pass through. So only water can pass across this membrane. And so what you find is that water will pass back and forth across the membrane, but it goes into the solution faster than it goes from the solution into pure water. Now you could also, in this case, they have pure water on one side, a solution on the other side. You could also have just two solutions with different concentrations on either side of the membrane. But always you get a net flow of water into the more concentrated solution. And in this case, that means you get a net flow of water onto the right. And so the picture on the left shows that after osmosis occurs, you can see that there is greater amount of water on the right side because there has been a net flow of water into the solution. To calculate the osmotic pressure for the solution, osmotic pressure, we give the symbol pi. So we have the equation pi equals mRT, and this is very similar to the ideal gas equation. Remember, if you take the ideal gas equation and solve for P, it's nRT over V. N over V is just the concentration. So we've replaced N over V here just with the molarity. And so you can solve the osmotic pressure. R here is just the gas constant. And if you use the same R that we used in gas calculations, then you can see that it has atmospheres in it. So that would give you the osmotic pressure of a solution of a certain concentration at a certain temperature in units of atmospheres. Now, osmotic pressure, you probably come across this in biology. It's very important in a lot of areas. It's how our kidneys function. Also, trees use osmosis. It's a way that they can take water from their roots up and say, for example, to the leaves of a tree, even going against gravity. The osmotic pressure can cause that to occur. Now, one last point I will make is that, so go back to the picture from the textbook I showed you before, and we said that the osmosis causes a height in the right side here, and that causes a certain pressure. So osmosis will occur until the pressure due to the height of that column balances out the osmotic pressure. If you apply a pressure, however, greater than the osmotic pressure pi, then you will reverse the flow of water, and so water flows across the membrane out of the solution into pure water, and that's known as reverse osmosis, and that's extremely useful because it is a way of purifying water. Now in the lab, you were sometimes told to use RO water. The RO there stands for reverse osmosis, and so that's just tap water that has been purified by reverse osmosis. You can also buy water from those machines by the supermarket, and one way they purify the water in those machines is also through reverse osmosis. But more importantly, you can actually even turn seawater, salt water, into drinking water. And in some areas, they have reverse osmosis plants next to the ocean that will take seawater and convert it into pure water. So reverse osmosis is a way that you can actually remove solute from water and make pure water. Okay, last thing I'm going to talk about, section 5, is how we apply the colligative properties to electrolytes. So for example, if you have a solution of salt, sodium chloride, and you measure its molality and then measure a colligative property such as the freezing point lowering, you find that you'd be off by a factor of 2. Now I mentioned at the beginning that the extent of colligative properties depends on how many solute particles are dissolved. Now we learned that when sodium chloride dissolves in solution, it's an electrolyte and it dissociates into sodium ions and chloride ions. So for example, if you take 1 mole of sodium chloride and dissolve it in water, you're going to get 1 mole of sodium ions and you're going to get 1 mole of chloride ions. And notice that is 2 moles of ions in total. So that is why the freezing point lowering of sodium chloride is twice what you'd expect, because you make 2 ions for each unit of sodium chloride. So when we deal with colligative properties of electrolytes, we have to consider how many particles the compound dissociates into, and that is known as the Van't Hoff factor I. So we can see for sodium chloride, we would say I is 2, because 1 mole of sodium chloride makes 2 moles of ions. So we can modify all the equations we've seen for the colligative properties, so you have to multiply them by I. So the freezing point depression of sodium chloride, you have to take the K times the molality times 2, since I is 2. So again, I is always the moles of particles you get when 1 mole of compound dissociates. We can do another example, and this is going back to really to reviewing when we first studied electrolytes earlier in the semester. Let's think about magnesium nitrate, MgNO3 twice. So if you take 1 mole of that, you're going to make 1 mole of magnesium ions, but you're going to make 2 moles of nitrate ions, which is 3 moles of ions in total. So I equals 3 in that case. So whatever the concentration of magnesium nitrate is, you have to multiply it by 3 to calculate the colligative properties. So in summary then, for any electrolyte, for all the colligative properties, when you calculate the colligative properties, you have to multiply the colligative property by this I factor, the amount of particles that the substance dissociates into.